Hi everyone, in this video we're going to learn how to integrate using substitution. So how do we know when we're going to have to use a U substitution? Well, we're not going to be able to just use our normal power rules or other known antiderivatives. So we're looking for products or quotients that can't be separated or expanded out. And we're also looking for what could be written as a composition of functions. The key observation here is to use this technique, you have to make sure that the derivative of the U value that you choose, whatever you're going to plug in for that U value, it has to have a constant multiple of the rest of the function. Here we want to find the integral of the quantity x plus 2 raised to the fifth dx. Now, I could brute force this and I could multiply out the whole thing x plus 2 to the fifth power, but that's going to take me a little while. So here I can recognize that this is actually a composition of functions. And I'm going to call this function here h of x. And I'm going to say that that can be rewritten as f of g of x. And if I decompose that function, I would say g of x is the x plus 5. And f of x is x squared. So when I do this, I'm going to make a substitution. So now I could rewrite this function a little bit as that this is the integral of f of g of x times the derivative of g of x dx. And that's true because over here, if g of x is x plus 5, I can say g prime of x is equal to 1 dx. So this would work. And then I can restate this and say this is the integral of f of u du. So this would give me the integral of u squared du. And we know how to take that integral. This would be 1/3 u to the third plus c. Now the other way to do the same type of problem, instead of going through and thinking about your decomposition of functions, is to make a straight up U substitution. So I can say, well, this piece here, the x plus 2, is what's getting raised to the fifth. So if I let U equal x plus 2, and then I take the derivative of that, du would just be 1 dx, I can rewrite this whole integral as u squared du. And that gives me, notice, the exact same thing we got here, but without quite all of that notation. So I tend to usually just work with my U substitution instead of decomposing the function. But you want to do whatever works for you. Here we want to evaluate the integral of x to the fourth divided by the square root of x to the fifth minus 17 dx. Okay, well, I notice that I have an x to the fifth down here and an x to the fourth up here. So what I'm looking for is how can I break them down? So I'm going to say let my u equal x to the fifth minus 17. So then du will equal 5x to the fourth dx. Now I can see I already have the x to the fourth dx in the problem, but in order to replace it with a du, I need this missing 5. Well, I can't just throw a 5 into an equation, but I can do anything that's equal. So I can take the original integral and I can multiply by 5 divided by 5, because this is just equal to 1. So rewriting, I'd have the integral of 1 over 5 times 5x to the fourth dx over the integral of the square root of x to the fifth minus 17. And now I can do that substitution, and instead of writing x to the fifth minus 17, I can use u. Instead of writing the 5x to the fourth plus dx, I'm going to plug in du. So my substitution becomes the integral of 1/5 du over u. 1/5 is a constant, so I can pull that out front. So this is 1/5 the integral of du over u to the 1/2. Sorry, I forgot my 1/2. So I'm going to rewrite that as 1/5 the integral of u to the negative 1/2 du, and then I'm just using my integration rule. So this is 1/5 times 2u to the 1/2 plus c. And then remember, we have to unsubstitute. I'm kind of running out of room here, so I'm going to come up way over here. So this becomes 2/5 times x to the 5th minus 17 to the positive 1/2 plus c. Let's try another. Evaluate the integral of cosine x over sine x dx. Well, I need to figure out which I want to be my u. Well, if I make u cosine x, the derivative would be in the denominator, so that's not going to help me. So I'm going to make my u equal to sine of x. So that makes my derivative, du, equal to cosine x dx. So when I'm substituting in, my cosine x dx here is my du, and my u is going to be in the denominator. So this becomes the integral of du divided by u. And from our other video on dealing with integration of special functions, our natural logs, we know that this is the natural log of the absolute value of u plus our constant. So this becomes the natural log of the absolute value of sine of x plus c. Okay, let's try one involving an exponential function. So I have the integral e to the sine x over secant x dx. Well, we know how to take the integral when it's just e to the x, so if this sine x was a single variable, that would help me out. So I'm going to start by saying u equals sine x. So that means that du equals cosine x dx. Well, we might be saying, wait a minute, we have a problem, but remember, 1 over secant x is actually equal to the cosine of x. So if I rewrite this problem, I can really say I have e to the sine x times cosine x dx. And now I can see I can do my substitution. So this is the integral of e to the u du. So when I take my integral, I get e to the u plus c. So this is e to the sine x plus c. Now when we're working with a definite integral, where we have bounds for integration a and b, we can still use our substitution method. We just have to remember to change these bounds according to our u substitution. So here we want to evaluate from -1 to 1 the integral of 3x squared times the square root of x to the 3rd plus 1 dx. So anytime I see a radical, I usually try to think the piece underneath is probably going to be what my substitution is. So let's check it out. So u equals x to the 3rd plus 1. So du will equal 3x squared dx. Okay, so that works. So I need to figure out what u of 1 would be, right? So u of 1 would just be 1 to the 3rd plus 1, which is 2. U of -1 would be -1 to the 3rd plus 1, which would be -1 plus 1, which is 0. So when I shift this and I write it in terms of my u, I'm going to say that this is equal to the integral of u to the 1/2 du, but now my bounds go from 0 to 2. Okay, so I do my integral, so this is going to be u to the 3/2 times 2/3, but I'm evaluating from 0 to 2. So I have 2/3 times 2 to the 3/2 minus 2/3 times 0. So this is 2/3 times 8 to the 1/2. So this becomes 2/3 times 2 radical 2. So my final answer would be 4 radical 2 over 3. Now, if you don't change your bounds, once you did your integration right here, you would have to plug in the x to the 3rd plus 1 and then reevaluate. So by changing my bounds of integration here, it just saves me a little bit of work. All right, let's try another one. So I have the integral from 0 to 1 of r to the 5th over 3 plus r to the 6th dr. So I'm going to say let u equal 3 plus r to the 6th. So then du equals 6 r to the 5th dr. Now I can already see that I have a problem because I'm missing that 6, but remember I'm allowed to multiply by a 1. So I'm essentially multiplying by 6 over 6 here. So then I'm going to have my 6 r to the 5th dr, and I'm also going to have a 1/6 that I'll end up pulling out front. I also want to change my bounds, so I'm going to find u of 1, which is 3 plus 1 to the 6th, which is 4. And I'm going to find u of 0. So this is 3 plus 0 to the 6th, which equals 3. So now I'm going to change this. So now I have the integral from 3 to 4 of 1/6, that's this guy, times du over u. So pulling out my constant, I have 1/6 the integral from 3 to 4 du over u. So this is one of our special ones. This is the natural log. So this is 1/6 times the natural log of the absolute value of u evaluated from 3 to 4. So this is 1/6 times the natural log of 4 minus the natural log of 3. Now I can use my properties of logs. I can condense this a little bit. So this is 1/6 times the natural log of 4/3.